Hello, everyone. So we continue with Chapter 6, Modeling Real-Life Phenomena. Specifically, we are now going to go into Section 6.3, Cubic Models. So cubic models are slightly more complex than quadratic models. We often encounter cubic models when we are dealing with quantities based on volume, such as optimizing the volume or surface area of a package or calculating forces from wind or water. Cubic models are also widely used in computer graphics in everything from modeling the curves of the letters in this textbook to smoothing computer-generated effects and animation. In this section, we will examine cubic models of the form f of x equals ax cubed plus bx squared plus cx plus d. Now remember that a, b, c, and d in this case represent constants or numbers. Note that a simple cubic model, as in the next example, may have b, c, and d equal to 0. In that case, it can also be considered a direct variation model, which we will study later in this chapter. So we start with example 6.8, and it says, the maximum theoretical power that can be generated by a wind turbine can be modeled by the function P equals 0.297 AdV cubed, where P is power in watts, A is the area swept by the turbine blades, swept area, in meters squared. D is the air density in kilograms per cubic meter, and V is the wind speed in meters per second. A certain wind turbine has a swept area of 80 meters squared, and it is located at sea level where the air density is 1.225 kilograms per cubic meter. Part A, find the cubic model for this wind turbine. So they are telling us that the model is P equals 0.297 times the area swept times the density of the wind times the velocity cubed. So what we have to do is substitute here for the area and the air density. So notice that we're going to get P equals 0.297 times 80 times 1.225 times V cubed. And from here we get that P is equal to 29.1 V cubed. Now notice that this is to three significant figures as usual. So this would be our model for this particular wind turbine. For part B, it says use your model to calculate the maximum theoretical power generated when the wind speed is 10 meters per second. So all we have to do is substitute the velocity for 10. So then P is going to equal 29.1 times 10 cubed. So this is 29.1 times 1,000. In other words, it's going to be, in this case, 29,100 watts. For part C, it says, given that wind speeds above 20 meters per second are strong enough to cause damage, give a reason why this turbine will not produce more than 300,000 watts. So what happens when the power generated is 300,000 watts? According to our model, we could say that 300,000 is equal to 29.1 times the velocity of the wind cubed. So we can solve for V here, for the velocity, and we can see if it's going to be over the 20 meters per second. That is the safe speed for the wind. So notice that we can divide 300,000 by 29.1, and we're going to get 10,309 is equal to the velocity cubed. Now, that means that the velocity is equal to the cubic root of 10,309, and this is going to give us that the velocity is approximately 21.8 meters per second, which is obviously above the 20 meters per second considered to be safe. So we can conclude that this turbine will probably not even get to 300,000 watts. For part D, it says find a reasonable domain for this model. So the domain is dependent on the velocity of the wind. And we just said that it can be from 0 up till 20 meters per second. So let's continue with example 6.9. And it says, the dimensions of a piece of A4 paper to the nearest centimeter are 21 times 30 centimeters. It is possible to create an open box by cutting out square corners and folding the remaining flaps up as shown in the diagram. So notice that here you mark 4 fold lines, which are the dotted lines here, equidistant from the edges of the paper. Then you cut out and discard the corners, and then you just fold up into an open box. Part A, develop a cubic model for the volume of the open box that can be created using this method. So notice that here the independent variable is x, which represents the amount of centimeters that we want to cut out from the corners of the A4 paper. So whatever x is, notice that the length is now going to be 30 minus 2x, right? Because if this is x and this is x, then we're going to be left with 30 minus 2x. Likewise, for the width, we can say that the new width is going to be 21 minus 2x. And then the height is simply going to be x. So that means that because the volume of a box is equal to length times width times height, we can say that for this particular case, the volume is going to equal 30 minus 2x times the width, which is 21 minus 2x, and this times x, which is the height. For part B, it says, determine a reasonable domain for your model. So obviously x must be greater than 0, right? Otherwise it wouldn't make any sense. But what would be the maximum for x? Now, the maximum, theoretical maximum, would be half of the width. Otherwise, we would be left with nothing to fold. So 21 divided by 2 is 10.5. So x has to be a value between 0 and 10.5. For part C, it says, find the dimensions of the open box with the largest volume that can be created using this model. So for part C, we are going to use the GDC. So here we are with the GDC, and what we're going to do is that we're going to graph our model, the cubic model. So we go to y equals, the volume is length times width times height. So we said that the length is 30 minus 2x, so 30 minus 2x times the width, which we said is 21 minus 2x, and this times the height, which is simply x. Okay, now normally when we want to do a graph, we have to make sure we have the right window. But I'm going to show you an easy way to get the right window with a function in Zoom. So you go to Zoom and scroll down to the 10th option, which says Zoom Fit. Click on Enter. And there we have our model. Now, this represents the volume. So the maximum volume is somewhere around here, right at the top of this curve. To find that maximum, we go to Second, Calculate, and then option number 4 says maximum. And notice that it says left bound. So that means that we have to move the cursor to the left side of what we believe is the maximum. So we move it to the left. Notice that the cursor is right there to the left of the top of that mound, so to speak. Click on Enter. Then it says right bound. So we move it to the right of that top or that maximum. And there it is. So click on Enter, guess, hit Enter, and there it is. Notice that it says that the maximum occurs when x is equal to 4.0559. So we can round that to three significant figures, and it's going to be x equals 4.06. Now recall that we said that the length is equal to 30 minus 2x. So that means that the maximum length would be 30 minus 2 times 4.06, and this is going to give us that the length is equal to 21.9 centimeters. Likewise, for the width, we said the width is going to be 21 minus 2x. Therefore, the width is going to be 21 minus 2 times 4.06. And then from here, we're going to get that the width is equal to 12.9 centimeters. Okay, so now for part D, it says calculate the maximum volume of the open box. We already have the answer to that because the maximum volume is this y coordinate. So notice that this was part C. So this is part D now. For part D, it says in the GDC that the volume is equal to 1,144.167. But because normally for these IB tests, we want to write this in three significant figures. So the volume is going to equal 1,140 centimeters cubed.